In this video, we're going to look at doing proof by induction on summations. If you've seen any other of the proof by induction videos I've done, the structure is going to be very similar. There's just one step that's a little bit different when we get to the inductive step. But the overall setup should look similar if you've seen any others. So, as always, I'm going to start just by stating my claim explicitly and labeling it. You could get away with this step, but I'd recommend doing it just as somewhere to store for you as well as for the reader. So our claim here is that the sum from r equals 1 to n of 1 over 2r minus 1, 2r plus 1 is equal to n over 2n plus 1. I should note proof by induction isn't the only way of doing this proof. You could do this by method of differences, but if you get this in an exam, there's a good chance it's going to tell you what method they want to see. So if it says proof by induction, you need to be comfortable with that method. Okay, so as always with a proof by induction, our first step is going to do the base case. So we're going to let's label it as such. So the base case is always considering the smallest value that we're interested in. So in this case, it's n equals 1. So if we consider n equals 1, let's look at the left-hand side and right-hand side of our claim and check they're equal. So the left-hand side of our claim is just replacing again with 1. We're doing the sum from r equals 1 to 1. So this is a very boring sum of 2r minus 1, 2r plus 1, 1 over that. And then we're just summing r equals 1 because it's the only term we've got. So we're doing 1 over 2 subtract 1, 2 plus 1, and this is just 1 over 1 times 3, or 1/3. And the right-hand side is just replacing m with 1 on the right-hand side of our claim. We just get 1 over 2 times 1 plus 1, which is 1 over 3. And encouragingly, the left-hand side and right-hand side are equal here. So we're going to make sure we stay that. Left-hand side equals right-hand side. So the claim is true for n equals 1. You can either say for n equals 1 or when n equals 1. That wording isn't that picky. Sorry, I should definitely say the claim is true though. The claim is true for n equals 1. Okay, now we've got n equals 1, we want to make an assumption. We want to assume that a claim is true for n equals k. Again, this step, you do need to be careful about your wording. You don't want to say just assume n equals k. You will not get a mark for that, and that will stop you getting later marks as well. So we're saying assume the claim is true for n equals k, and then we're going to say explicitly what that means. So that is, and all we're doing here is going to our claim and replacing any n's we can see with k's. The r's are staying as they are, but we're saying, well, the sum from r equals 1 to k of 1 over 2r minus 1, 2r plus 1 is equal to replacing n with k on the other side, k over 2k plus 1. And now we've assumed it's true for n equals k. We're hoping in that case it's true for n equals k plus 1. So let's consider n equals k plus 1. And let's write down what we're hoping to see. So this next line, you can get away without writing, but it's really useful for yourself to see what we're trying to aim for. So our target, all we're going to do is we're going to look at our claim, which is up here, and we're just going to replace any n's now with k plus 1s. All the r's are going to stay as they are. So our target, we're hoping that we can prove that the sum from r equals 1 to k plus 1 of 1 over 2r minus 1, 2r plus 1 is equal to k plus 1 over, and at this stage I'm not going to simplify the bottom, I'm going to write it explicitly with n replaced with k plus 1. So yeah, it doesn't look like a very nice form, but we want to make it explicitly n just replaced with k plus 1. That's what we're hoping to prove. Okay, so let's start with the left hand side of our target. Let's write what that is, and then this is where we have one clever step we have to use, and it's the only really clever step in the whole of proof by inductions with summations. Sorry, my writing is just going to be dodgy there. I'll just rewrite that a bit more legibly. 2r minus 1, 2r plus 1. Okay, so this is the one step where we're saying, well, how are we going to make use of our assumption? Our assumption is this thing here. We're saying that the sum from r equals 1 to k of this thing is k over 2k plus 1. We need to make use of that. The only way we can make use of it is by splitting this up. We can say that the sum from r equals 1 to k plus 1 is the same as the sum from r equals 1 to k of this thing. And then, well, what do we need to add on? We need to add on the k plus 1th term. That's what's not included in the summation. So we're going to have plus, and then at this stage I'm going to explicitly replace r with k plus 1 just to show what's going on. You could try and simplify all in one here. It's just taking a bit of a risk. So this thing here, and you don't have to label this, I'm going to use a different color to label here. So the bit in green you definitely don't have to write, but that thing there is the k plus 1th term. All we've done is replace n with k plus 1 there. Okay, so now, well, what have we assumed about this sum from r equals 1 to k? We've assumed it's equal to k over 2k plus 1, so let's make use of that now. Let's replace that first thing with just k over 2k plus 1. That's our inductive assumption. And now let's simplify this second term. So expanding those brackets, our first bracket is going to be 2k plus 1, and our second bracket is going to be 2k plus 3. At this stage, it's worth looking at our target. This is where our target comes into play. We want a single fraction. That's the main thing to see. We have two fractions at the moment. So how can we make a single fraction? Let's make a common denominator. The lowest common denominator we can make is going to be 2k plus 1 times 2k plus 3. So we can leave that second fraction as it is, but the first, we're going to have to multiply top and bottom by 2k plus 3, and I'm going to combine these straight away over 2k plus 1. 2k plus 3. There's nothing natural to do now straight away to get here. So looking at our numerator, well, it's worth noting our denominator is two factors here. We're expecting to have one factor, so we're hoping for some simplification to happen. We're going to have to expand that numerator and then see if we can simplify it another way. So expanding, we're getting 2k squared plus 3k plus 1 all over 2k plus 1, 2k plus 3. And now, hopefully we can factorize that, so the numerator, because if we can, we're going to be in business. This numerator is going to factorize to 2k plus 1. K plus 1, you can check that, but that should work out nicely. And now we can simplify what we've got. This fraction is just going to simplify down to k plus 1 over 2k plus 3. We're almost there. Let's go back at our target and see what we're hoping for. We're hoping for k plus 1. We've got that over, and we just need to rewrite our denominator to explicitly have n replaced with k plus 1. So that denominator, we're just going to write as k plus 1 over 2 brackets k plus 1 plus 1, and that's the form we wanted, and now was the right-hand side of our target. So we managed to show you don't need this equal, that's RHS there. Okay, so only thing we need to do now is conclude. Conclusion is going to be exactly the same as if you've done any of the other proof by induction videos. So the first step is so if the claim is true for n equals k, then the claim is true for n equals k plus 1. So note, we're not saying the claim is true for n equals k and n equals k plus 1. We're saying if it's true for n equals k, then it's true for n equals k plus 1. That if-then structure is vital. And then the second thing we want to say is, since the claim is true for n equals 1, the claim is true for all positive integers then. Or you could just say for all n greater than or equal to 1, given that's the way the question was worded. It's implied that n's got to be an integer here. You could just say all positive integers if you wanted to be more careful though. Okay, so just to summarize what we've done there, just to go through those steps. So state your claim, do your base case, check the left-hand side of equals for n equals 1, as long as you're told that's your lowest value you're interested in. Assume the claim is true for n equals k. Like I say, common mistake there is just say assume n equals k. This wording is vital. You will lose at least 2 marks on the question if you word that badly often. So we're then considering n equals k plus 1 and saying what we're aiming for. This is the unusual step for summations here. So we're saying the sum from r equals 1 to k plus 1 is the same from r equals 1 to k plus what happens when we replace r with k plus 1. So that's the step that only comes up with proof by induction summation questions compared to other proof by inductions. From there, it's just following your nose with the algebra and making sure you finish with then explicitly replace the k plus 1. Okay, thank you very much.